Potholes are endemic in cities. Freeze-thaw cycles, friction, and general aging are all causes of potholes. Manual reporting of potholes is not incentivized and is slow. Pothole crews can't be sent out if they don't know where the potholes are, and searching for potholes takes valuable time.
This is Pothole, our solution made up of an automatic pothole detection and mapping system. The product is designed to be able to mount onto street sweepers and other city vehicles. We use a combination of deep learning cameras to detect potholes and ultrasonic sensors to measure pothole dimensions. Then, the mapping system can take the output of the detected pothole and display the location, width, and measured depth. Hi, I'm Jonathan, and I'm a member of the hardware team working on ultrasonic sensors and mechanical design. To measure the width and depth of potholes, ultrasonic sensors were chosen for their simplicity and repeatability. We started testing with a small array of 3 sensors with individual enclosures, and this system was able to measure distances quite accurately. Moving on to implementation on a street sweeper, a larger array would then be needed. An aluminum channel frame was constructed to match the dimensions of the street sweeper, and 10 ultrasonic sensors were then mounted on it using 3D printed parts. 10 sensors are mounted at a 60-degree angle downwards for optimal performance. A wiring harness was then completed and secured to the new ultrasonic array. This was connected to our electronics enclosure, which is mounted on the roof of the vehicle. This enclosure houses a Raspberry Pi, battery, GPS sensor, and a camera for our deep learning system.
I'm Samantha, and I'll be going over the deep learning component of the system. Deep learning was used for visually detecting potholes on the road surface. Current ways of detecting road damage rely on the post-processing of collected images. We decided that in order to have a real-time detection system that would be easy to use by local road workers, an object detection algorithm is the best option. For our product, the placement of the camera that is retrieving the image data is of high importance. Placing it in the dash of the vehicle could result in a glare effect off the front windshield, which would affect the model's ability to correctly identify a pothole. The object detection algorithm used was MobileNet version 2 for its high frame rate and sufficient accuracies. A Google Coral USB accelerator such as this one here was used in order to speed up the frame rate for operation of the model within a Raspberry Pi. Now, here is a video recording of the Pi camera recording a street with many potholes. The camera was held by hand outside of the window of a car traveling 10 to 20 kilometers per hour to get a sense of how the model would behave with a moving vehicle. And here is a video of a final proof of concept system driving over a pothole. The camera is now securely mounted at a fixed position and angle. The car is driving at the expected speed of a street sweeper, which is about 6 kilometers per hour, and the model is running at a frame rate of about 10 to 20 frames per second, which is more than sufficient for real-time object detection while the vehicle is moving.
Hello, my name is River, and I am going to talk about the GPS component and system integration of pothole. The GPS sensor is used to get the location of potholes, as the repair crew need to know where the potholes are. This is how the GPS sensor is connected to the microcontroller. The antenna has to be kept outside of the enclosure because of the weak GPS signal. When the GPS sensor is on, the data from it is passed through a decoder. Then the decoded information will be saved into a file for the web application to use. Whenever a pothole is detected, location information for this exact moment will be saved to file. The ultrasonic sensors are activated at the same time and will stop when the uneven surface is detected. Based on the returned values and the separation between the sensors, the approximate width and depth are calculated and saved to the file.
Hello, I'm Evan, and I'd like to introduce the mapping portion of our project. Once the potholes have been detected, we use a combination of the Google Maps API and Firebase in order to show the potholes to the user. I'd like to show you how we process our data. I would like to show the Google Maps window. Google Maps is a ubiquitous and pervasive mapping system. With it, we can show pothole locations. The API can also show updated business info as well as transit information. To sync pothole locations, the Google Maps API syncs with a database. The chosen database is Firebase, which integrates readily into the console window. Each user is anonymous and can affect the database individually while all the changes are synced.
Hi, I'm Elvira. I'm going to introduce our user design. If we enter in the full address, we get a marker pin on the map. The system uses geocoding to convert addresses to coordinates. If we enter in latitude and longitude, We also get a marker pin. Here is the appearance prototype of finished website. The sidebar will show more information on the pothole markers in the map. It will show latitude, longitude, time of detection, width, and depth. The user can enter in address manually and select size and depth. The system will read in the reported time automatically. The user can also enter in text file with latitude, longitude, and geolocational time. Thanks for watching.